Well, I think we've reached the end of our 10-minute segment. So time to get back to the Shine type presentations. And the first one is supposed to be from Dushan Ojtersil. Dushan, are you in the audience? And if you are, can you raise your hand so that you can be unmuted?
Dushan, you are a co-host. You should be able to unmute and share. And Dushan is in the list.
Okay, can you hear me now? Hello.
Yeah, we can hear you. Yeah.
Okay. Can you show my PDF presentation and I will just talk? Or
yeah, I can bring it up for you.
Yeah. Or maybe I can share the screen. Or probably not. Or we can go for me might be better.
Yeah, I'll do it. Just a moment. Let me get it going.
Yeah.
Okay, can you see your presentation, Dushan?
Yeah, I hope it. Yeah, yes. Okay, so if everything is fine, then I will start. So
yep.
I was making some global simulation of the global structure just to try to differentiate what might be possible and eventually if the shock can form within the co-rotating structure. So there were two different cases shown on this first title page. Both are co-rotating, meaning that there are static structure basically of the fast and slow stream. Low speed is blue and high speed is orange in this case. So there is some tilted dipole that I was providing data and results previously. I was making some parametric study I was providing to Kurt and others. So this was a static configuration of the well-developed stream structure. And on the right side is actually new ones that might be more realistic during some cases. There is just single small case coronal hole. And there are actually differences in between those structure. And I will show on the next slide. Next slide is that basically on the left, there is a view in those equatorial or ecliptic plane. The red is high speed. Now, solar wind accelerates, so is a high speed stream that co-rotates and interaction happens. And on the right side, you see profiles through velocity structure. You see that there is basically a regular pattern between low and fast speed, but on those interaction region, actually you can develop as on those bottom line as profiles at 3AU. Actually, you see the shock structures. There are those double jumps. Basically, you have the forward shocks. There is some incline level, and there is a reverse shock, and then there's again constant high-speed stream. And these structures can eventually be seen maybe at 2AU, but very difficult. And I will show example in 1AU. So next slide. Next slide, you can see the same with those coronal hole, and you see that basically there is the same structures, that same interactions that leads to forward and the reverse shocks. And actually, there is first difference. The previous one, actually, there is very static structures that eventually you can see up to Jupiter and farther out. Basically, there are co-rotating interaction regions. There is a consistently there, but this one eventually you can decay because on the right, actually, there is some rarefaction wave trailings that actually eats up from this fast stream, and then you can have some bump-like structure, and there is no shock pair structure, the 5AU in this case. And the next slide, you see that actually how it is difficult to observe co-rotating structures in YAU. Also, Lanjan reported there were very weak occasional structures, and it depends on numerical grid resolution. I use the blue, basically the different columns corresponds to half AU, center is 1AU, and right is 2AU, and there are different colors. Low resolution is 4 degrees angularly, and medium resolution is what is used in those operational forecasting is 2 degrees angularly, and you see that it is not enough to make some resolution very good at the central column at the 1AU. So you have to go high resolution black and fine resolution green that eventually can see some signature, some potential of origin of the shock structures that is much better seen on the rightmost column as at 2AU. The next slide, and there will be one. Next slide is actually that how it might be actually different to go. There are two synthetic light images for Tile deposit. Actually, it is very difficult to see those structure. Also, they are very static and stable. They are very good for global structure and heliosphere, but to visualize them, to see them in static, because those interaction dense structure actually goes up and down. How to say? There is no continuous integrations of planes. Therefore, it is the best seen from those S at 0.02 that starts red lines. On the right is the density, the view of the density in ecliptic plane, and the red lines are those basically the 30, 60, and 90 degrees elongations that are shown on the left. You see some dark structure that you see those density and structure, and on the right, on the last one slide, basically you see the same for coronal hole, and this one is actually better seen because there is some continuous, the structure interaction happens in the same plane. The other goes up and down from those visualizations. Therefore, it is there, it is very good, but not for imaging. But this one is maybe narrower, but it is much better seen in those wide light images. And you can see that it's very well developed structures, followed by density, followed by some rarefaction region. So that's all basically just to provide that it's possible to visualize those structures, but it is difficult to see shocks within 1 AU. So thank you for attention.
Okay. Stop sharing that. Okay, so is there any questions that come out of that presentation? And in particular, again, if there are, please enter your questions into Slido. And from there, we will be able to read them out. Everybody will be able to see them, comment on them.
Yeah, I have a question for Dusan. I just asked it in the Slido. Dusan, it was hard for me to make out. There were lots of little features in some of those CIR front simulations. In the Slido, I asked if they were locally produced, but I guess I need to also ask, are they real? Are those artifacts, or do you think that they're reflecting something physical going on?
No, this one simulation was very global. That's a very global structure, but I can simulate some substructure when I learn some blob-like structures that may emanate from some reconfiguration of magnetic field reconnections of stream caps, basically. And actually those stream structures, what can be simulated by blob-like corresponds roughly with 1 hour cadence that is observed by the other guys, and they are actually helpful to trace global structure. But this substructure can be a real one, but meaning that this one was too global just to demonstrate origin of the shocks. It is difficult to achieve them in such low quantities.
Got it.
Okay, if there's not any more questions, then we'll go on to the next Shine Style talk, which is from Craig DeForest.
Ah, since I happen to be hogging the spotlight anyway.
Since you're hogging the spotlight, you might as well continue. Did you want to do your own presentation, or shall I bring it up?
If you don't mind bringing it up, that would be the easiest.
Okay. We'll make sure we can actually get it to work this time.
All right, so while this is coming up, I'll point out so little is known about CIRs in detail. I'm kind of struck, that this is, I said it at the beginning, maybe the largest discovery space available for PUNCH is in this area. Just CIRs have been measured a bunch of times, but unlike most of the other features we talk about, especially space weather relevant features, they haven't really been subjected to these cross-scale and large-scale analyses that every other part of the solar and heliospheric system has been, and largely because of technical difficulties, right? It's just hard to image them. So can we go to the next slide, please? There are a lot of basic things that to my mind act both as signs of, if you will, dark clouds on the horizon, things that are of interest that we're not at yet, and others that act more like, something out of a Conan Doyle book, you know, a dog that should bark but doesn't. An example here, this first slide sort of shows, this is a Pizzo and Gosling drawing from 1994, showing, you know, an artist's conception or an informed scientist conception of what a CIR might look like in the equatorial plane, right? Looking across as PUNCH will. And you can see there are a couple of different fronts here, and they have sort of complicated curvature, but they look sort of S-shaped. We see some structure here in the Ostrasil model in 2009, Ostrasil and Pizzo, of course. You can see various bits of material coming out at different heights here. These envelope plots, of course, most of us know how to read them at this point. The left one is looking down, the middle one is looking more or less like part of the punch field of view. Oop, could we go back for a second? Thank you. And then the right is a time plot. Anyway, so, okay, now let's go forward to the stereo movie. Thank you. So this is, before we even run the movie, this is an image of a CIR. And there are a couple of papers that have been called out. The Woods paper is excellent. The Williams paper is great. The Riard paper is excellent. That's basically all there is about these large scale structures. The first thing I want you to see is this CIR, which extends in this still frame as sort of, the sun's off to the right, it's extending as sort of a quasi-ellipsoid that's almost contacting Earth here, of bright stuff. There, thank you. The front of that looks rounded, and it's rounded, it's concave toward the sun. It doesn't have a significant S shape. There's a north-south gradient here that's kind of obscuring the bottom half of it. But it looks, I like to describe it as an Archimedean snail shell. And just the fact that it has that simple shape is really remarkable. It looks almost nothing like what we're seeing with these multiple puffs in the Enlil or in the artist conception from the 90s. It's much simpler, but also, you know, why is that? You wouldn't, these fronts are formed by pileup of fast material on slow material. And so there's no particular reason why the front should have any particular shape. My intuition was it would be concave away from the sun because wind speeds are higher near the pole. And so I would expect if you have a constant difference between two streams and both streams are going faster toward the pole, it ought to take longer for them to pile up. That was obviously wrong. But there's something going on here that's making this shape that I don't think has been adequately explained in the literature. Okay, can we run the movie? All right, so as this goes, I hope this repeats. It sometimes takes a few views to sort of pick out the details. Uh-oh, I'm so sorry, you're gonna have to keep clicking that. The first thing you see are there are several white arcs there that come out at the beginning. And that sort of could be a scalloped shape to the front. It could be waves going through the front. We just don't know. If they're small compared to the distance between the observer and the feature, we can locate them in 3D with PUNCH when we see similar things with PUNCH. If running this a few more times, let's just run 3 or 4 more times. Oops, sorry.
About that one.
Yeah, okay, here. There's a lot of interior structure that comes out. You can sort of see there are, on multiple views, you can see there are little sort of domes of brightness that form and push through the front. There's one right there on the just north of those arcs. Let's play this one more time just to see that. So look, just north of those arcs as they go by, and you'll see a little sort of dome that pushes out. Is that an ejecta in the solar wind? Is that an inhomogeneity where there's a puff of faster wind that's piling up better? I don't know. There's a lot to be seen. If you look carefully at the structure, there are a lot of stranded structures in here that are reminiscent of coronal loops. There's one right there in the final frame. So Kurt, if you could move the cursor sort of halfway between the Earth and the sun, about, and then down a little bit, down into the right, a little more right there. Okay, right above that, you'll see a little dark lane between two bright features.
Sure.
In the movie, that a little bit left of that, it's just a faint little lane, hard to see. In between. There, right there. Yeah, sorry, I should have operated the slides. That persists over several frames. That's a real effect. That's not just in that frame. so that's pointing to a lot of substructure that just isn't visible yet, and a lot of rich physics that's going on. Waves being launched, maybe little patches of shock forming, inhomogeneities in the solar wind. There's just a lot. There's a big playground here to play on. There's a lot that we just don't know. And these are important because, as we learned earlier, these are the most common source of space weather. And so, because there's so much unknown, I think we really do need some forward models, Duchamps, and some that include more structures, even though this is sort of the wide open and it's hard to constrain just what to simulate. I think we need to do that and try out some models. And my last slide here, and then I'll open the floor up. If we go to the next one, this is a cautionary tale describing what happened down in the low corona over a period of, oh gosh, well, this is just 14 years, but it's been going on for about 20 years. Trying to understand what's going on with coronal loops in the EUV, right? I have this 07 paper I like to cite that has some really stupid models of single and double stranded loops that I ran through a forward model and showed that Trace couldn't tell the difference, even though the loops were allegedly resolved. That's part of a debate that's been going on for a long time. My sense is that Anna Malinushenko, who's on this call, has really sort of clinched that discussion by pointing out that there may not actually be coronal loops at all. What you're looking at here is a moving cross-sectional plane through a detailed simulation of coronal loops. And although there are loops visible in the forward model that's projected on the back of that figure at left, in the cross-sectional plane, which is displayed face on at right, you can see there really aren't any. There are wisps and veils, and most of what you might attribute to being a compact loop in the structure is in fact mostly a perspective effect. So I think we need to be aware and to do studies with punch data or simulated punch data to understand what punch won't tell us about these features, these structures. Otherwise, we run the risk of falling prey to the same kind of, if you will, paradigm trap of thinking of particular features in the way that's most intuitive when we view them. So I guess that's all I had to say. It's just there's a lot to see, and there's dragons there too.
I see Vic has a question, so go ahead, Vic, or a comment.
Yeah, I want to say, well, that simulation that was on the left, that was for a totally idealistic situation where you have a perfectly flat current sheet, and you just that was aimed at just describing the overall dynamics of what happens at high latitudes. That was as far. There was no substructure whatsoever in that, and given the way the model works, if you don't put in any substructure, you're not going to get any out of there. I mean, until you get shocks, that's the only substructure you can get. So, but that's unrealistic because that had to be, I mean, that would probably be, even at that time, a fairly warpy kind of current sheet with bumps and wiggles on it, probably not dead steady. And especially, I suspect that as you go further out in the simulation, the effects of having more variation at the start would probably get bigger. This is just as smooth as possible rendition of that dynamic that was intended there. So there's no detail there.
Sure.
It's not very good representative of what you would be seeing with an instrument.
Absolutely right. You're talking about the 94 sketch or the 2009 sim there?
And I guess maybe I have a question for Craig too. I mean, what was that? I don't know, getting some kind of delay here.
Yeah, Vic, maybe you want to turn off your video. I think you may be running into lag issues.
Yeah, it's off actually. Or at least it shows as being off. But yeah, I was going to ask a question about. Yeah. Yeah, I'll ask you later. This is just not working.
All right, maybe we could take it to Slido. The text will work.
Okay, yeah, Pradeep, you want to go ahead with your questions, comments?
Yeah, I have a couple of questions. First question is related to the CARs. So Craig pointed out that the CAR that was discussed in slide number 3 doesn't seem to resemble the cartoons or the NLIL models. But I also posted this question. Now, most of the structure would be projected in and out of the plane. So we would not be able to catch, let's say, the full 3D view of that CAR. And could we comment on the structure that is only seen part of it and then try to get the full picture? Is it possible? Because we do not have the full 3D information of the CAR.
Are you asking about this data set or about Punch?
No, this data set, because you mentioned that this particular CAR doesn't look like what has been projected in the cartoons or in the models. Now, the question was, most of the CAR might be hidden in the plane, fore and background. So could either Punch be able to resolve this 3D information, or can we get to the 3D information just by looking at part of it? That's my question.
Got it. I think it's very hard in 2D because they are fundamentally 3D structures, right? They're large Kirby planar structures embedded in 3 space. And that's exactly the kind of structure that an imager does poorly at. So with Punch, I think being able to resolve the 3D location of that front as it propagates will go a long way toward understanding these large scale structures. Right, each line of sight intersects a curvy planar manifold at one or a small number of points. So we ought to be able to get 3D structure out of that with Punch. And
if I may ask another question, that is related to the last slide where you talk about the loops or lack thereof. Now the question is, when you run the movie, yes, the bottom movie, where you skip through the axial direction of the magnetic field, because in axial direction, the magnetic field are basically points in space, you would never see a loop-like structure. They may just appear as bright dots depending on how emission is contoured around that field. So is the comparison of not having loops is accurate in this case, because you're not really looking at a field line in its, let's say, projected way, but in a point way, like you're really looking at its single point, not the whole field line.
We may want to ask Anna to step on here, but I'll point out that there are field lines rendered at left, and they correspond to those moving points on the plot at right. And so you can see that there are swirls and veils of plasma on loci that are very complex and not compact.
Yes. So now, if you maybe pause the movie somewhere here, you do maybe in the midsection where it's in the close to the axis, top loop axis. Yeah. So now, yes, yeah, you do have certain bright features on one side, on the other side of the yes, that one and the other section. Yes, these would be the loops, but then you cannot see them as loops, obviously, because you are looking at in the line of sight of magnetic field, right? But you do have a diffused corona in the model, and that is what is giving rise to the rest of the structure in your frame there, isn't it?
Well, I'd like to draw your attention to the projection on the left, right, which has very rich and detailed fine structure. And for example, this very tall loop that I'm tracing right now doesn't correspond to any particularly bright feature down below, right? In this frame, I think it's this little squiggle. Right, and so most of these bright edges that you see in the full forward model are they don't correspond to individual compact structures. That's the point I'm making, is that we have to be aware of pitfalls, right? Where if we see a compact structure in the solar wind, it may or may not actually correspond to something that we would normally think of as a structure.
Okay.
Anand, do you want to go ahead and offer some additional insight into your work? You do need to unmute.
Yeah, Kelvin, if you could please unmute Anna Malinushenko. Her hand is up.
Hi, yeah, it didn't let me unmute myself, for which I apologize. Yeah, so one thing is that the line of sight here, the integration is done along the line of sight, which is not the magnetic field, if I understood you correctly. It's just the dotted direction along the in the volume. Then one more thing is that those bright structures, I mean, they do appear as loop bundles. That's the thing. But as the rendering here shows, those bright structures, they do seem to be aligned along the magnetic field lines. It's just that the thing is that they are not thin, compact. They're not thin, compact like bright garden hoses filled with stuff, if that makes any sense. And that figure that Craig tried to outline, the loop that Craig tried to outline, Craig, that part of the volume is actually shown a little further in the movie. You are looking at the loop bundle that's on the left. So that wiggle on the line of sight integrated image that you showed with your mouse, yeah, this one, it is further away in the movie. Yeah, there we go. That's perfect. And there is this kind of lightning, yeah, that structure seems to, I mean, when you integrate it along the line of sight, which is in this case horizontal, you do get something that looks like a loop on the, well, forward modeled image. And the forward model image is just the sum of this, of the right panel along the line of sight, if that makes any sense. And the line of sight is horizontal. I don't know if I'm answering your question.
No, you're answering. But here the line of sight is also matching, let's say, the major axis of the magnetic field. So you are looking at a structure in a tube. Through the tube, you are not looking the tube from the sideways, but actually looking down the barrel, right? In all the
so the image in the back shows the line of sight integration that is actually horizontal.
Yes, that I understand. I'm talking about the veils that Craig pointed out. Yes, exactly that one. Those structures. Now those are looking down the barrel of the magnetic field. So you do not always get to see the full loop. You will only see a cross section of the magnetic field in that plane, right? That's my point.
You're seeing the cross section of plasma in that plane.
Yes, exactly.
And this bright structure seems to be the cross section of the magnetic field done by this like the cross section of the flux tube that contains this bright structure. Now, if you go to the subsequent slice, you will see that the same structure is more or less preserved. So just really it's a magnetic flux tube with this cross section. Yes.
So you do have a loop. You have a bundle of structure that is preserved the whole length of it. No.
So yes, and it is tempting to say, well, it's just the loop that has this weird cross-sectional shape, right? The problem is that as soon as the structure will start rotating about its axis, what will show up in the projected image? In the projected image, you will see two loops, or no loops at all, or some background, or something very weird. And
yeah.
This association between this flux tube with a weird shape and the loop on the line of sight projected image is kind of breaking down once you let it.
Yeah, that is non-intuitive. Yes, I agree.
Okay, Noor, you've had your hand up for a while.
Yeah,
go ahead?
Sure. It goes along what Pradeep was talking about, and basically most of it was kind of addressed. But my question, I'm just curious if what I'm gonna say just makes sense. Well, denying the existence of loops, I don't think that's. I don't think I would not even go there. So loops exist on the corona. There is no question about it. But Anna, are you saying that when we are looking sideways to the loops, face on to the loops, what the emission highlights is basically the proxy for the magnetic field, but when we are looking at the other direction, mostly what we are seeing are the thermal effects?
Anna, you're a co-host, you can unmute.
I'm trying to understand the question. So, can you explain your question actually?
Okay. So when you are looking face on to the loops, like the background image there, what you are looking there, you are looking at the plasma that is tracing the magnetic field. Basically, it's a proxy for the field. But when you look at the other direction, which is 90 degrees from there, what you are looking at are just the mixed thermal thermal effects that you are getting from the plasma.
So yeah, so you're looking at both ways. So you're referring to this vertical plane that is kind of side on, that is crossing the loop bundle. If you're referring to this plane, then yeah. So this plane is basically the mixture of thermal effects and plasma effects. The problem with the other view, the backdrop plane, is that it is the integral of the other plane. It is the integral of the plane that is going across the loop. Makes sense?
Yeah. Yeah. So just to understand, and for the right-hand side panel, are we integrating along the line of sight there, or it's just the intersection?
It is just the intersection. It is the integrand. It is the thing that you integrate to get the forward modeled emission.
But are you integrating along the line of sight there also or not?
No, it's just simply the volumetric emissivity.
Then we are missing something there. The corona does not work that way. The corona is optically thin, and you have to have the line of sight even in that plane. You cannot just take the intersection and say, yeah, this is my emission, and I should find the structure where it is.
So in the point of this is that this, at least in the context of this meeting, is that here is a geometry that Anna has discovered in the MURAM models that mocks up very fine scale compact loops. Mm-hmm. The geometry, when integrated horizontally here, makes structures that look very much like compact loops. But in fact, in this structure, right, the geometry is very different from the compact loops we might come to expect from the image. Right, and that's the only point I really want to explore here. I've been letting the discussion go on because it's very interesting and important from the standpoint of understanding that geometry can do very weird things, right?
Yes.
Whether the corona really works this way or not is something we can discuss at a different meeting at more length. Mm-hmm. But insofar as how observations work, I think this makes a very compelling point that the telescope, right, in this case, the integral through Anna's figure on the left, tells us something that is immediately, it has a visceral response, right? Our visual system identifies these fine features, which simply are not present in the cross-sectional plane.
Yeah, I asked about the thermal effects because I think there was a paper by Hardy Peter a few years ago, where he also ran a simulation. And when you look at it, you think they are loops. But actually, when you look at the physics, actually there are thermal effects. There is no magnetic field there.
Right. They cross magnetic field lines, right? Because the contours of brightness don't match the contours of the continuum field.
Yeah. Mm-hmm. This is interesting. I have to read the paper. I have not read it.
It's really brilliant work. It's one of those things that once you've read it, you think, why didn't I think of that? It's well worth a read.
But denying the existence of loops is a huge claim.
Can I make a comment about that? That's exactly what I raised my hand to say. I think you want to be clear what you mean by loops, nor do you mean the loops as in the field line white thing that's drawn there, or do you mean the loop as in the assumption that the bright EUV structure you see is compact and has essentially a small aspect ratio in its longitudinal direction? And those are two different things. And I don't think there's a question here that when you have a bipolar magnetic field, the magnetic lines of force go in a loop-like direction. Mm-hmm. But the question is the plasma organized in a very coherent and compact way along that loop?
That's why I used the word proxy earlier. So proxy does not necessarily mean that the plasma is tracing the fields point by point.
Right. So when
but
you
the
say
overall picture reflects what basically the field is kind of doing, but not necessarily tracing the field lines 100%.
Right. And I actually have a follow-on that, and to try to bring us back to CIRs. So the analogy, I'm just going to throw it out there, see where people take it. with the loop, you have the magnetic lines of force, and you know, as I said, you know the direction is going to go from
Yeah.
one magnetic pole to another. And that's guiding a lot of our perception and interpretation of what we're seeing in this line of sight integrated emission. Similarly, with the CIRs, we have the Parker spiral, we have the fact that the sun is rotating, and then you have fast and slow wind, and that's what's making those beautiful spiral patterns, like in that second slide there in Duchamp's models that we see, looking from above. And so the question is, is it because of that particular view? And the question I would like to ask Duchamp is, the middle image there, which is like Punch's field of view. So it's not looking down from the pole at the spiral, but looking at the structure coming out. What is Duchamp's interpretation of the observations that we've seen Craig showed in the next slide? And then conversely, maybe to ask Craig or maybe to ask whomever, what do they think we would actually see if we could look from above? That makes sense as a question, or two questions really? So Duchamp first. Duchamp, what is your interpretation of this?
Duchamp, are you there to answer? I don't know if you have to raise your hand to be unmuted.
He is a co-host. He's able to unmute, and he is here with us in the list. He might be away.
He may have stepped away.
But you want to take up some of the questions? I know some of the question was for you, Craig.
Yeah, and actually, Craig, I'm going to throw one more into the mix because I put a bunch on the Slido. Can you explain what the heck you mean by the shell, the Archimedean shell, and how it relates to this?
Sure. Okay, so I'll do that first. What if you look down at these spirals in Duchamp's simulation, right? It takes the form of a shell, or the shape of a spiral in the cross-sectional plane there, in the equatorial plane. And that's sort of well captured by the cartoon that we saw. But what does the structure look like in 3D? Well, what we can see from that movie is that if you come out of the plane, the spiral gets closer to the sun. And that's sort of the same general shape as the outside of a snail shell, right? That it sort of spirals outward, but it's round in cross-section. Of course, I call it an Archimedean spiral shell because, or snail shells, because snails really have geometric spirals and not Archimedean spirals or logarithmic spirals, and not Archimedean. So here, what you're looking in the plane, right, and you're seeing an arc here, and I'll put it on a frame near the middle so you can actually sort of see the arc of the CIR. And so in the cross-sectional plane, it's sort of bent, it's concave toward the sun, and it's bent around like the outside of a snail shell. It's coming out of the plane toward you and bending around. We see these multiple arcs, which are probably different parts of the shell, and scallops, if you will, in the shape of the outside, but they could also be bright fronts propagating through the shell, right? These data can't resolve whether they are, which of those is the right model. Does that actually sort of help?
I want to see a visualization done, a 3D visualization done, but you know that.
All right, let's write a paper. You and me and Kurt. But I think that it's actually really important. We need to start thinking in terms of making forward models of that shape and variance thereof so that we can explore, if you will, this null space of the measurements. What kinds of things can we see and what can't we? Even if there isn't any physics in the model, just rough kinematics, it's worth doing to see what we see through forward modeling. I'm sorry, I'll hand back the mic. Sarah, did you get your question answered?
Yeah, and unless Duchamp's here too, or anybody else want to follow up.
Duchamp, are you there to chime in on your model, your results?
Yes, I'm here.
Yeah, did you hear the question, Sarah's question?
No, not fully. Could you please repeat? Or?
Yeah, Sarah, you want to go ahead again?
Sure. I'm basically asking, do you think, so the image in the middle is the view of Punch, right? The one from the pole is the one that shows that nice, very conceptually straightforward spiral pattern because of the sun rotating in the fast and slow wind. But it's a little harder to visualize and understand that edge-on view. And then if you go to the next slide, Kurt, So this is what Craig was showing. And I was just wondering your own interpretation of this structure. Do you feel that your model can you see your model in that? Do you think that if not, is it because of line of sight ambiguities? Is it because of dynamic or structural substructure that's not in your model? And just what's your interpretation of these observations?
Yeah. So first, you questioned previous picture, but in the middle there is no view for punch. Basically, it is a meridional slice. It is the same 2D plane slice from north to south.
Right, you mean it's not integrated along the line of sight?
Yeah. And this depends because there might be two effects. First is so-called Thomson surface, and another is also some beam surface, because eventually you can integrate rotating structure. You can acquire much more from stereo A, how to ahead view, than from the stereo B in the past, basically, because you was looking to skim, basically to tangential integration or to integration through. So therefore there might be two spatial effects that you can add. And because of this one, actually, I can observe in simulations that some structures overlap, or they are catching up with each other. But maybe I can try to simulate some specific dates just to try to provide some hypothetical structure starting from WSA and others. This is what I would like to ask for this period of time, that to Craig. Basically, I will try to, as it might be possible to replicate something like this one.
I'd love that. Let's do it.
Yeah,
I don't know. And we are running a little bit behind at the moment, or nearing the end of this session. So James and Vic, if you want to chime in, let's start off with James. Chime in and see. I think you need to unmute James, or be unmuted.
James looks to be unmuted. He might be having issues with his audio.
Otherwise, Vic, if you want to go ahead while James.
Yeah. I just two things. One, I want to know, what is the date of this simulation that's running right now? What time period is that?
Craig, do you know what date you took your?
Yeah, it's that first. It's right after that first geoeffective CME. So it's December of what, 09 or something? Of 08.
Okay, so
yeah.
It's a time ramping up to solar max, but it's early before that.
Yeah.
And then the other comment just would be, I mean, this is line of sight integrated, and it's hard here to tell what's front, what's back, how deep you're looking, how many features you're looking through, etc. And certainly any observation like this, you're going to have a lot more detail going in than you're going to have in any model.
Yep.
Okay, we are at the end of our section, James. If you had any additional comments, if you want to put them into Slido, then we can capture them there. But it looks like Craig and Sarah are saying we really should move forward onto the next set of presentations, the student presentations. Sorry about that, James. So I think, Steve, you were going to introduce the student presentations.
Yeah, no, I'd be happy to. Yeah, this is this presentation is on the STEAM module, which is defined in the talk. This is the student collaboration that we decided to add at the concept study level for PUNCH. And Craig had the awesome idea to go to the Colorado Space Grant Consortium here in Boulder that works with undergrads from around the state. And here we have Gabriela Galarraga, Samantha Honan, and Sarah Bordiuk. One of you can share your slides, and I think we made you all co-hosts.
I got it.
Yeah.
All right.
I don't quite see the slides yet. Oh, there they are.
Okay. Is it visible for everybody?
Yes.
Yep.
Okay.
Sure, go ahead.
All right. Hello, everyone. I'm Gabriela Galarraga.
I'm Sarah Bordick.
I'm Sam Honan.
And we will be representing the STEAM team today. And so, as you heard, STEAM is the Student Energetic Activity Module, and we will be measuring the key enhancement of elements and temperature in solar flares and solar active regions in both soft and hard X-rays in order to distinguish signatures of distinct signatures of reconnection-based coronal heating mechanisms.
So STEAM's main science objectives are to explore and classify the enhancements of key low first ionization potential elements in the corona by looking at the sun with both hard and soft X-rays. Through this classification, we will be exploring the mechanisms of how solar coronal plasmas are heated in flares and quiescent active regions. Both of these goals will support PUNCH science by helping to understand how the spectral properties of flares correlate with the source regions of the solar wind and coronal mass ejections that PUNCH will observe. So currently, it's not well understood how the corona is heated during solar flares and in non-flaring active regions. But one of the current leading theories in science is that of magnetic reconnection. During this process, once enough energy is built up, the magnetic field lines get twisted and then rearrange themselves into a lower energy state. This twisting and reconnection results in a rapid release of energy in the form of flares and nanoflares that suddenly release heat and energy into the corona, thus heating it up. And some atoms in the corona are easy to ionize, and we call these low first ionization potential elements, low FIP elements for short. And typically the abundances of these low FIP elements are enhanced by a factor of 4 in the corona over their chromospheric values, which can give us clues to where the plasma was heated based on their measured abundances, which in turn allows us to distinguish between different coronal heating models. STEAM's main science objectives are to classify by how much low FIP elements are enhanced in flares and active regions, and then infer the origin of the heated plasma through our findings. And these low FIP elements also emit soft X-rays that I will explain the importance of in this next slide. So why exactly are we measuring X-rays? Soft X-rays provide the most direct signatures of hot plasma and are highly sensitive to hot temperatures, as well as fluctuations in temperatures. We can also expect little to no contribution from colder chromospheric material, which will help in our data analysis. And also soft X-rays are easy and simple to measure using spectroscopy. STEAM will also be measuring hard X-rays, and this will extend our thermal continuum to cover higher energy bands over 10 keV. And hard X-rays assist in providing a more complete picture of the plasma evolution. By using both soft and hard X-rays in conjunction with each other, we will gain a more comprehensive understanding of coronal plasma's temperature and composition. And so right here is a visualization of the X-ray spectrums of some elements in the sun, with spectral intensity being represented by relative brightness. And on the y-axis is the log temp in Kelvin, and the x-axis is the wavelength in angstroms. And the elements with the white labels that you can see here are the low FIP elements that I was talking about earlier. And the red labels are high FIP elements, but we will specifically be focusing on the low FIP elements circled in that blue circle there. And STEAM will be observing similar low FIP spectral lines as MINCS, but we will have greater resolution, energy coverage, and temporal coverage.
Okay, so how are we going to measure these X-rays? Well, STEAM is flying one soft and one hard X-ray spectrometer, both of which measure individual incident photons and their energies. On the bottom of this slide, you can see the interior and exterior of one of our detectors. The entire device, for reference, is small enough to fit into the palm of your hand, and the actual detector head, that's the little red round thing, is about the size of the tip of your thumb. And so these spectrometers both measure in 10-second integration periods, and they assign photons into appropriate histogram spectrum bins based on their energies. So on the top right, this video that's playing is a representative example of what this process looks like, where the red line represents each individual histogram, and that white line represents the spectrum achieved from summing the histograms together. which we do to improve statistics. Again, this video is just a representation for the actual STEAM mission. We will be adding up histograms as is necessary to get good statistical results on the timescale of about a minute for flares and at least every 6 hours for active regions, as defined by our requirements. So the data shown in this video is from NASA's MINX mission, and it represents a flare in the soft X-ray. The yellow line represents change during that flare, and you can see the enhancement in the continuum as well as those key spectral lines. So this video was put together by NASA, and it is an example of what STEAM will likely see for a flare in the soft X-ray, but STEAM will have a better sensitivity and extend into the hard X-ray range. So on the right of this slide is a CAD model of the interior and exterior of STEAM with its dimensions shown. As mentioned before, it'll house 2 X-ray spectrometers. So both of them are off the shelf, and we will be using a silicon drift detector to make our soft X-ray measurements and a cadmium telluride detector to make our hard X-ray measurements. And as Sarah mentioned, observing in both hard and soft X-ray allows us to capture a wider range of emission, which extends our sensitivity and our energy capture range. So the soft X-ray spectral resolution is sufficient to determine key emission line clusters, while for hard X-ray, we only need to resolve the continuum, as there aren't many significant low FIP lines falling in that range. Our requirements shown on the bottom left of this slide outline the field of view as being between 5.25 and 10 degrees, which limits background radiation, but also accommodates for pointing uncertainty. And the other requirements shown in this table are the minimum for our energy range and resolution. So we expect them to be even better than the values listed here. The 2 photos at the top of this slide represent how STEAM is going to fit into the NIFI satellite, which is the PUNCH spacecraft that will carry the solar coronagraph. And the blue wall represents that NIFI solar panel, and the orange arrow is pointing to STEAM. So as you can see, STEAM is looking out through a cutout in the solar panel, so it will always be facing the sun. And on the bottom of this slide are 2 photos of our prototype build of STEAM. The whole prototype build, for reference, is approximately the size of a tissue box, and it's currently sitting in our lab space, and we have test fit those PCBs and have been conducting preliminary testing on it. So we will be doing on-ground pre-flight calibration of our spectrometers using radioactive isotopes to determine energy scale, energy resolution, and spectral response. With energy scale, we will be specifically looking at gain and offset values, and spectral response tells us about the attenuation of X-rays through the filters that we will be using and their absorption in the detector. So the diagram on the bottom left illustrates each of these things. And given that we know the energy of the emission lines we're seeing from the isotope, we can determine which channel number corresponds to an energy, thus giving us our energy scale and offset thus giving us our energy scale and gain and offset values to calibrate. And from the width of the line, we can determine our resolution. And from the height, which is the number of counts we get compared to the number of counts that we're expecting to get, we can determine the spectral response of our detectors and how well the X-rays are being captured by them.
So here's a little image of how we plan to achieve our science goals, as well as how we plan to process our data. So one of our goals is to measure the temperature and elemental abundances in solar flares by observing X-ray photons and measuring their respective energies. And so then we would take that information and then model our observations with the appropriate physics. And so we will be building a spectra for the flares where the continuum regions will be associated with free bound radiation and free radiation, or Bremsstrahlung radiation. The emission lines are then going to be associated with the bound radiation. And so then for the analysis of the spectra, the shape of the continuum and the intensities of the lines of the emissions will allow us to fit temperatures and abundances to the spectrum of each flare and active region. And so we'll be doing this by using forward modeling and iterative chi-squared minimization with the Bremsstrahlung and atomic emission databases to derive those physical parameters from our observables. Okay, so this data, which is courtesy of Minx and Resi, is very similar to what we expect to see and do with STEAM's data. So by using both a hard X-ray and soft X-ray spectrometer, we will have a larger range of sensitivity. As looking at the graph, you can see that the soft X-ray spectra gets a little bit noisy when overlapping with the hard X-ray range. And so by having both of them, it allows them to complement each other and fill in the noisy parts of their respective spectrums. And then the gray box near the bottom right is data that is outside of our detectable range, since our hard X-ray spectrometer has limited sensitivity over 30 keV. And so we'll be utilizing emission models to plot each colored dotted line, which will represent one thermal component of the temperature of our distribution that fits the spectrum. And then the hard X-rays allow us to fit the green and blue line accurately and better constrain our continuum, whereas the soft X-ray allows us to fit the brown line accurately. And so putting it all together, it gives us an indication of what the low FIP elements are doing. And through our forward modeling, we can yield the red line as shown, which represents the line of best fit for the whole spectrum and tells us the temperature and elemental abundances that the data will represent. And in the future, when we get our actual data from the spacecraft, we will be using a more sophisticated forward modeling method. So the field of view for STEAM will include contributions from the cosmic X-ray background. And in order to see how this is going to affect our science, we modeled an example flare and active region in both soft and hard X-rays, soft being on the left and hard being on the right. So we had found that the cosmic X-ray background would not be a significant source of uncertainty for either flares or active regions in the soft X-ray, contributing less than 1% of the solar flux. For the hard X-ray, we will be getting significant counts from the flare. And then for the active regions within the detectable range of the hard X-ray, the cosmic X-ray backgrounds would actually be too low to be measured. And this is what we expect our data pipeline to look like. For our level 1 data, our products would be downloading from the spacecraft and then converting it from binary to a more user-friendly format such as FITS. Our level 1 data product would be to calibrate our data based on the exposure time and the instrument response. And then our level 2 and 3 would be to convert from counts to photons and sort our data into the different time averages. And then finally, our level 4 data would be to combine our level 1 with models to help us derive our physical parameters. And so additionally, all of our data is going to be open and available for anyone to use, and STEAM is always happy to help anyone navigate it if they have any issues. And so, as mentioned before, one of our science goals is to support our parent mission PUNCH's science objectives, and much of the science we'll be doing is actually very complementary to that. And so STEAM will be observing the energetic processes and the plasma heating of the corona that provide the source regions of solar wind outflows that PUNCH will observe. And so together, these two missions can give us a better understanding of the processes between the corona and the heliosphere. And some work that we are currently doing, once again mentioned before, is the spectrometer calibration. And in addition to that, we are currently in our final design and fabrication phase, having passed our PDR. Currently, we are working on developing an engineering model and with a critical design review phase in October. Thank you so much for listening to our presentation, and we're open to any questions that you may have.
Fantastic. All right. Do we actually have any questions? People can raise their hands or put their questions into Slido. Craig.
So I'll put a question to Slido too, but do you expect to see strong and prompt responses to CME events that aren't flare associated, or are you primarily looking for flares and nanoflares?
That's a good question. Currently, we're just kind of focusing on those flares and nanoflares as well as their active regions. I'm not quite sure about the CMEs. If Sam or Sarah knows, they can answer that better.
Well, certainly enough to look at for flare events with an X-ray spectrometer. Thank you guys very much. That was a great presentation.
Sure.
Yeah, as I put in the chat, I saw this presentation more than once, and it's really outstanding. You guys are amazing, so it's really fantastic. One question is, okay, I think the main focus will be big flares, but when you look at small scale, there is a lot of flares also, but they are smaller. They behave like the large scale flares, but they are just smaller. Can you guys resolve these flares, and what can we learn from them?
Well, we're able to look at the smaller flares because of our short integration time and our sensitivity. Some flares, though, will be kind of too small for us to detect, like some of the photons just won't make it to the detector. So if that happens, that just kind of happens. Okay. But with our 10-second integration time, it wouldn't affect too much of our statistics or our modeling of the flares as a whole.
Interesting. Thank you.
Sarah?
Thank you. Great job. It's just coming along, just like Nora said, every time it's getting more and more advanced. Yes. And I think we're ready to really start digging into the question of how we're going to work together with the punch observations, the white light, and maybe look at some of the, you guys have looked at some of the MINX observations, for example, and try to get some idea of like how are we going to relate a big flare and the CME that we're observing with punch. And then maybe there are smaller scale, mesoscale structures or observations that you're going to see that we can connect to some of these features in the solar wind that punch is going to uniquely be able to analyze. So I think we definitely we'll get together and we'll start talking about that, because it's the complementarity is great, and we're really excited to see what you guys are going to be doing.
Yeah, thank you. Yeah.
All righty. Well, we are just about 20 seconds early for on our schedule, which is great. So yeah, we have 10 minutes in the schedule for a wrap up. I don't know if that's enough time to go back to Slido and to start going through some more questions. I don't know if either Kurt or then also Sarah and Craig have any final wrap up comments for the day.
I think, yeah, we want to make sure we have time to do just the usual wrap ups, but we can take a moment or two and make sure we haven't missed anything big. I'm mostly going to just go over what's going to happen tomorrow, make sure to remind people about some of the survey that we're talking about, that kind of thing. That's what I was just leaving with. Craig, did you have anything else?
Just to thank everyone for the great discussion all day. We had four major topics, excuse me. We had STEAM is working backwards, CIRs, a lot of discussion about the Alphane zone, and some really great insight into observing effects that we need to be aware of. Lots of great back and forth, and I'm thrilled that everyone was able to participate so well.
Yeah, and moving forward, what we're going to be doing tomorrow is we've got 2 more talks by our associate investigators. And then we have our last 2 working groups in a super group, which is the CMEs and the shocks. We'll probably have opportunities to connect to some of what we've already talked about in terms of for example, some of the CIR fronts. We'll figure out those synergies as we go. And then the other thing we have tomorrow is we'll be talking about punch in the context of the Heliosystems Observatory. And then the other thing I wanted to make sure was brought up now was the survey that, can we throw that in there one more time, Michelle? I know it's been coming by a couple times. So there's a survey that we're encouraging people to do at any stage during the meeting. Does anybody have anything they want to raise? Because we do have a little bit of time.